Let's talk about partial pressures of gases. And the question is, what's the effect on total gas pressure when two or three gases are put together in the same volume? Let's consider this illustration. Gas pressure is measured, of course, as the force of a gas per square meter. And the Pascal is a Newton per square meter. Pressure is produced by these fast gas molecules hitting the walls of the container that they're in. And if the temperature is constant, that pressure will remain constant as long as it doesn't leak. Let's look at a second situation. Consider a second gas at the same temperature in the same size container. The temperature is the same, so the kinetic energy, according to kinetic molecular theory, is the same. If the molecules are smaller than our first example, then they must also be faster, so that the same number of molecules can have the same pressure. Now, if we combine both gases, they will occupy the same space, and each one will exert the same pressure as before. But now, there are more of them. We've got two gases exerting the pressure that they had been exerting in the same size container at the same temperature. Thus, the pressures will add linearly. This leads to Dalton's law of partial pressures, and it's the same John Dalton who gave us the atomic theory, or at least his expression of it. Dalton stated that the pressure of a gas mixture is the sum of the partial pressures of all the individual gases, or total pressure equals P of the first gas plus P of the second gas plus P of the third gas plus however many gases there are. Now, liquids often have a vapor pressure. We know that's true, for instance, for alcohols, because if you, say, open a bottle of rubbing alcohol and waft it towards you, you will smell the vapor of the alcohol. You have a liquid phase down here at the bottom of the tube or the beaker, and up here you have the vapor phase of that same substance. Now, here is a illustration, a diagram graphing the vapor pressure of various liquids at temperatures ranging up to 120 degrees Celsius. And at 1 atmosphere outside pressure, it also gives us the boiling temperature, which we know is 100 degrees for water. For ethanol or ethyl alcohol, it's 78.5 at 1 atmosphere. And for diethyl ether, which is what you may have heard is used for anesthesia in some primitive places, the normal boiling point is just 34.6 degrees Celsius. So the vapor pressure of the diethyl ether at any given temperature is much higher than of alcohol and even of water. Now, how can we use that? Well, if we have a table of the temperature versus the vapor pressure of water, this can be very useful to us in the laboratory. Sometimes we will create a gas in a chemical reaction, and the gas bubbles up from the reaction and is taken over by a tube into a collection vessel. The gas will bubble up into this water-filled container. It will push the water level down, but the gas is, we say, wet, because it's not just the gas we've collected, say hydrogen or oxygen, it's also the water vapor that it's picked up as it bubbled through the water. So this wet gas must have a higher or lower total pressure than the gas that came out of the reaction. I think the obvious answer, it's a higher pressure because it's the sum of the pressure of the produced gas, say hydrogen, and the water vapor. So it gives us a practice problem to do. Here's our vapor pressure table. If the atmospheric pressure is 104 kPa outside and the hydrogen gas in a cylinder inverted in water is at 24 degrees, what is the pressure of the hydrogen gas alone? So the pressure of the hydrogen gas must be the total pressure minus the water vapor pressure, which at this temperature, 24 degrees, is 3 kPa. So we would subtract the water vapor pressure from the total pressure and get a hydrogen pressure of 101.0 kPa. This was what we would be using in a calculation, because the water, of course, will not act the same way as the hydrogen. Here's a second practice problem. Air is 19% oxygen and 80% nitrogen. If today's atmospheric pressure is 98 kPa, what is the partial pressure of oxygen gas? The total pressure is equal to the pressure of the two. We'll ignore the carbon dioxide, water vapor, and anything else that's in the air. So, the pressure of the oxygen must be 98 kPa minus the 0.8 mole fraction that is attributed to the nitrogen. 0.8 times 98, or 0.190 times 98. The oxygen pressure is 18.6 kPa on this day. Remember, the mole fraction X is the number of moles of a particular substance in a mixture divided by the total number of moles. In a mixture of gases with a total pressure of 101 kPa, the partial pressure of hydrogen is 25 and oxygen is 50. The rest is nitrogen. So what are the mole fractions of all these three gases? We'll repeat the problem on the next page and show how it's solved. Avogadro's principle tells us that equal volumes at the same temperature and pressure contain equal numbers of molecules. That must be the case because all of these are contained in the same volume. So the volume fraction then is the mole fraction. And the mole fraction of hydrogen then must be 25 divided by the total 101, 2.247. Oxygen, 50 divided by the total 101. And nitrogen, 26 divided by 101, the total. So we have these mole fractions for these gases.